Welcome to Numerical Methods for Scientists and Engineers with Pseudocodes. Video 5. Cruel of Space Methods. Conjugate Gradient Method. The conjugate gradient method is based on minimizing the quadratic scalar function defined as follows. Where A is a symmetric positive definite matrix, minimizing the function f(x) yields the gradient of f, which gives ax equals b. The conjugate gradient method requires an initial guess, which we use this to compute the initial residual vector r, and we initialize the conjugate search directions d. These are the initializations before proceeding with the actual conjugate gradient iterations. Inside an iteration loop, we compute the step size using the following formula. Here, the notation of a pair of vectors x and y in parentheses refers to the dot product of the vectors. Then, the current estimates and residuals are updated as follows. Next, we check for convergence using the spectral norm of the residual vector. If the norm is less than a convergence tolerance value, the computations are terminated. Otherwise, the procedure is continued by computing a parameter beta and a new search direction. To set an initial guess, if a rough estimate for the solution vector x is available, it can be used as the initial value. Otherwise, setting x equals 0 should be sufficient for most cases since the conjugate gradient method eventually converges in at most n iterations. As for the stopping criterion, residuals at 2 iteration levels, current and prior, are available, so there is no need to specify absolute or relative error in terms of the displacement vector as in the cases of the stationary methods. The simplest and most common absolute and relative stopping criteria are based on the L2 norms of the available residuals at the end of each iteration step. One or both criteria can be employed at no additional cost as follows. The advantages of the method are: CGM is a simple method to program and easy to parallelize. Theoretically, in the absence of round-off errors, it yields the true solution after a finite number of iterations, as many or less than the number of equations. It converges, if it does so, with a linear convergence rate dictated by its condition number, that is, the smaller the condition number is, the faster the convergence will be. It is particularly suitable and useful for large sparse systems with regular patterns. The method has the following disadvantages. Conjugate gradient method is applicable to linear systems with positive definite and symmetric coefficient matrices. The method may exhibit instabilities even for small perturbations. The method is computationally more expensive in comparison to stationary iterative methods per step and requires more memory allocation. In large sparse systems, the rate of convergence may become quite slow unless an effective preconditioning is employed. In practice, the true solution may never be obtained, as most directions are not conjugate, or round-off errors due to finite precision arithmetic may result in a loss of orthogonality in the residuals. Consider solving the following 4x4 system of linear equations. We seek the numerical solution of the system of linear equations with the conjugate gradient method using x equals 0 as the initial guess and with 4 decimal place accuracy. The linear system in matrix form can be cast as follows. The initial guess is the 0 vector. Here, A is the coefficient matrix and B is the right-hand side vector. The initial guess vector is given. We use this to compute the initial residual vector, which is determined to be equal to vector b. The spectral norm of this residual vector is found to be 31.1769, which does not satisfy the convergence criterion. The search direction is initialized with the residual vector, which we will use to calculate the matrix A and vector D product, which yields Since the vectors R, D, and AD are available, we can calculate alpha, which is 0.11259. Using alpha and vectors X and D, we can calculate the current X vector as follows. Likewise, using the same quantities, we calculate the current residual vector. Having the first step residual vector at hand, we can check to see if the stopping criterion is satisfied. So we calculate the spectral norm of the current residual vector, which clearly does not satisfy the stopping criterion. To be able to determine the new search direction, we calculate the direction adjustment factor beta using the current and prior residuals. Having the beta value, we find the new search direction as follows. The product of the matrix A and vector D is required to calculate the step size alpha, so we obtain the vector AD. The vector R, D, and AD at hand, the step size alpha is found as. We can now compute the second step estimate as follows. And the corresponding residual vector yields the following vector. Now, we check for the convergence criterion. We determine that the spectral norm of the residual vector is greater than the desired tolerance value, which means that we should continue with the iterations. Before we find a search direction, the direction adjustment factor beta needs to be calculated, which is done as follows. Having R, D, and beta values, we calculate the new search direction. To calculate the step size, we need to update the product of matrix A and vector D, which gives. And the step size is found as minus 0.293931. The current solution vector is obtained as follows, and the corresponding current residual vector is calculated as follows. The spectral norm of the current residual vector is found to be 0.9957, which is greater than the specified tolerance value. Using the prior and current residuals, the beta value is calculated to be 0.00502. The corresponding search direction yields the following. The AD product is computed. Note that the magnitude of the resulting vector has significantly decreased. Next, we calculate the current step size alpha, which yields minus 0.989846. The current estimate leads to the converged solution. Here, the true solution is given with deviations in the order of the machine epsilon. With this, we imply that the results will be affected by the precision used in the computations. Similarly, the current residual vector will be 0 within the order of the machine epsilon. The calculations presented here were carried out in double precision, but rounded to 5 decimal places. The spectral norm of the current residual vector is obtained as 7.11 times 10 to the minus 14, which satisfies the stopping criterion. For a system of inequations with a symmetric positive definite matrix, the maximum number of iterations required to converge to the exact solution is n. Because the conjugate gradient method can converge in at most n steps for an exact solution in finite precision arithmetic, that is, in theory. Note that the system in this example converged in 4 iterations. For a positive symmetric coefficient matrix, an upper error bound for the pth estimate is given as follows. Where E denotes the true error, norm E is the spectral norm, kappa A is the spectral condition number. A simplified expression for the error bound is reduced to the following. And for positive definite symmetric A, the condition number is the ratio of the maximum to minimum eigenvalue. The performance of the conjugate gradient method is very good when applied to well-conditioned systems. That is, linear systems having a condition number in the order of 1. If a linear system is ill-conditioned, the condition number is much greater than 1. Then the numerical solution is plagued with round-off errors, affecting the convergence rate adversely. The technique of accelerating the convergence of a linear system by reducing its condition number is called preconditioning. A preconditioner, a matrix, is used to modify the original linear system so that it is easier and faster to solve iteratively. The preconditioned form of the matrix equation AX equals B is written as inverse P times A times X equals inverse P times B, where A is a symmetric positive definite matrix and P is an invertible preconditioner matrix. The condition number of the modified matrix is reduced by selecting a reasonable matrix P. The effectiveness depends on the condition number of inverse P times A. The preconditioned system is solved at each iteration step. Thus, the preconditioner should be selected such that the cost of solving PZ equals R is minimum. Preconditioning increases the memory requirement and computational effort, but the additional cost is compensated by the reduction in the number of iterations required to reach an acceptable solution. The algorithm covered so far is applied to symmetric systems. For non-symmetric systems, we can apply the conjugate gradient normal residual method or the conjugate gradient normal error method. That is all for now. See you next time with another topic. Bye.